Okay, hi everyone. For those of you that were here on Tuesday, welcome back. If you're new, then don't worry. Nothing I said on Tuesday is going to be important to understand what I am going to say today. So on Tuesday, we talked a lot about probability, and we learned about things called the law of large numbers and the central limit theorem. And we used those to analyze what I would call a zero-player game, which is roulette. And what we did is calculate the probability that you lose money on roulette and how much money you expect to lose. So today we're going to move on from what we talked about on Tuesday, and we're going to talk about multiplayer games. And we're in particular going to be focusing on non-cooperative games. So the other day when I was thinking about how I want to talk about this, I happened to be wasting time watching Instagram Reels, and I came across quite a fun introduction to this idea. So someone was posting this table on Instagram. So on the left, we have two actions that a person can say. They can tell their partner that they love them, or they can not do that. And the person, their partner, could say the same thing back. And these four combinations of things result in different people being happy or unhappy. So if everyone says I love you, everybody's happy. If everyone doesn't, then everyone's also fine, like they're indifferent to that. But if only one person does, then the other person gets upset. So what game theory gives you is a way to like make mathematical sense of this kind of situation, where different people who take different actions have different rewards based on what each other do. So if we were being really pessimistic about life, we could convert this into kind of a mathematical game where people get different outcomes in these different scenarios. So in the best possible case, everyone gets 100 points each, but in the others, different people might lose 100 points or get zero. So what we're going to develop today is kind of like a framework by which we can analyze tables like this with different payoffs and decide if everyone is behaving rationally, kind of what outcomes should people take in these games. So that's the goal for today. What I'd like to start off by doing is to play a game of rock, paper, scissors. So if everyone can go to the chat, there should be a poll sitting in there in the meeting chat. Can everyone see? It just says rock, paper, scissors, and there's three choices. Let me know if you can't see the poll. Can't see it. Owen can't see it. No one can see it. Okay, great. I'll create a new poll then. So the goal that you're trying to do is you're trying to be in the group that kills the most common uh, response. So if 80% of people said rock, you would like to have said paper to the poll. Let's have a look at the results. Okay, so if you said paper, congratulations. 22% of people said paper, 40% of people said rock, and 40% of people said scissors. So I think that's a win for paper. The numbers just changed towards the end. Uh, okay. Um, so do people type in chat? If everyone was playing rationally, what percentage of people should have said each outcome in rock, paper, scissors? Anyone have any idea? Yeah, lots of people are saying one third. Yeah. So what one third of people should have said each outcome. And that makes sense because if lots of people were saying rock, it would be in your interest to say paper. So then those people should not be saying rock, basically. I think that makes logical sense to everyone. And we'd like to kind of turn that into a mathematical definition. So let's do that. So first of all, if we're playing a game, what even is a strategy? Like, what does it mean to have a strategy? Well, a strategy should be like a rule where everything you've seen uh, up to now in the game, you take that into account and then you decide on the action that you'd like to play next. So, for example, if you're playing chess, you see all of the moves that have happened so far, and then taking all that into account, you find your next optimal move. So, a strategy then is like a mapping that takes into account everything that's happened so far in the game and spits out what's the best thing you should do next. Okay, that's what a strategy is. So it's a mathematically it's a function, and its input is like a history of the game, and its output is your next move. So in rock paper scissors, because the game only has 1 round, there is no history of the game. There's only 1 round. There's no history. So all a strategy is just an output of whether you should say rock, paper, or scissors for rock, paper, scissors. Okay. So what we would mean by a pure strategy is something like always say rock. So it's like a strategy that has no randomness in it at all. And what we'd mean by a mixed strategy is like what you're gonna say is random each time. So your strategy could be something like 40% of the time I'm going to say rock, 30% of the time I'm going to say paper, and 30% of the time I'm going to say scissors. Does everyone understand the difference between these two things? Thumbs up in the chat if you're happy. Yeah, okay, cool. So I'd like to give you a minute to ponder. If you were playing optimally in rock, paper, scissors, should you play a pure strategy or a mixed strategy? Feel free to type in the chat. And even better if you can type an explanation for why that's the case. Yeah, lots of people saying mixed. Can I get an explanation? Okay. Oliver's saying mixed, it's unpredictable. Mixed because you don't have a pattern. Yeah, okay. So what I'm going to claim is that even if you're only going to play one round of rock, paper, scissors, it makes more sense to be mixed. Mohammed says doesn't matter. Yeah. So for if you're only playing one round and you don't know your opponent's behavior, I agree it doesn't matter. But we're gonna make sense of what it means for the mixed strategy to be better. Okay. Yeah. So for example, if you knew your opponent was always going to play rock, then you would just play paper every time. Okay. So what is an optimal strategy then? So we've already claimed that in rock, paper, scissors, one third, one third, one third should be like the optimal thing you can do. And now we're going to try and find out why. So we're going to need the concept of a Nash equilibrium. This is a new thing that I'm going to define. So you're not expected to know what this is already. So a Nash equilibrium is a pair of both you and your opponent's strategies. So, for example, this could be like you saying, I'm going to play one third rock, one third paper, one third scissors. And it could be your opponent saying, I'm going to play half paper and half scissors. So, an equilibrium is a pair of these that has certain properties. Everyone happy so far? Thumbs up, thumbs down. So, when we say equilibrium, we just mean pair of strategies. Okay. Or when we say, yeah, configuration or strategy profile, all of these words mean pair of strategies. Now, what properties are there if everyone is playing optimally? Well, if I've decided my strategy and I know what my opponent's strategy is, I shouldn't want to change my own strategy. Okay, I think that makes sense. So, like, if I knew that my opponent was going to play half rock and half paper, then knowing that, I should be playing something that I don't want to change. Does that seem reasonable to everyone? So knowing my opponent's strategy, I shouldn't want to change my own strategy. And the same thing should go for your opponent. So your opponent should think that if they change their strategy, they'll do worse in the long run if we play this game over and over again. Seem reasonable to everyone? Okay. Okay, cool. So we're gonna introduce some sort of notation, some mathsy symbols now. So if my strategy is A, so that means like A can be like one third, one third, one third, or A can be 1-0-0, meaning I always play rock, for example. And my opponent's strategy is B, then we're going to define a quantity which is like what I expect to win, how many points I expect to win on average when we play this game. So for people from Tuesday, this is the expected value of the number of points I get. Imagine that I get 1 point for a win, 0 for a draw, -1 for a loss. So then U of these two strategies is my expected profit or my expected number of wins minus my expected number of losses. And we say that it's a Nash equilibrium if changing A and keeping B fixed decreases what I expect to win, i.e., I don't win more by changing my strategy. And also that my opponent thinks the exact same thing. So changing B while keeping my strategy fixed means that my opponent will score less. Is everybody happy with that definition? So I've written it down in kind of symbols at the bottom here. But what you need the main point is a Nash equilibrium was where neither of us want to change our strategy if our opponent keeps it the same. Okay, cool. People seem happy with that idea. So in which case, let's start looking at some examples and seeing if we can like tell when we're in a Nash equilibrium and when we're not. Okay. So I've already said that we're going to record a strategy in rock, paper, scissors as the probability you play rock, the probability you play paper, the probability you play scissors. So for example, in this case, 0.2, 0.7, 0.1. Okay. So if your opponent has decided to play the strategy 0.2, 0.7, 0.1, what is your best strategy? What is going to maximize your average score? Go ahead and type an answer in the chat if you're okay. Lots of people are saying scissors. So can you write that down in like the mathematical form that we've decided to use? Yeah, yeah, okay. So your best response to 0.2, 0.7, 0.1 is just to play 0, 0, 1. Okay. People seem happy with that. Uh, if we do that, then what is our expected score? What is the average score we'll get? So if we're saying one is a 1 point for a win, uh, minus 1 point for a loss. So that is my question is, uh, what is the probability we win, and what is the probability we lose, and what is the probability we draw in this game? Okay, so someone has said probability we win is 0.7, probability we lose is 0.2, and we draw otherwise, so 0.1. So what is our average score if we get 1 point for a win and minus 1 point for a loss? Yeah, someone has correctly said 0.5, which is the 0.7 chance we win minus the 0.2 chance we lose. Yeah. So on average, if we played this game over and over again, we're winning 0.5 points per round. Good. Okay, so our opponent probably isn't happy with this. Does everyone agree? So we're going to need to change our strategy that we're playing. Our opponent is going to want to change their strategy that they're playing, right? They're losing because they're playing paper too much. Okay. So the question is this configuration of strategies a Nash equilibrium? Remember the definition we had on the previous slide. Um, yeah. I'm not making a poll because polls were confusing. So yeah, no. Okay. Can people talk me through why it's not a Nash equilibrium? I agree. Yeah. So there, remember in the definition of Nash equilibrium, there are two things to check. First of all, do we want to change our strategy if we know our opponents? In this case, no, we're doing the best thing we possibly could be. And then there's the other half, which is if our opponent knows our strategy, do they want to change? In this case, what would our opponent want to change to? Yeah, our opponent would just play 1-0-0. Yeah, cool. Good. How about this? Okay, so lots of people are correctly saying no. I agree. This case is a little bit more interesting because in this case, our opponent is completely indifferent to whatever their strategy is, right? Do people see why whatever our opponent does, it makes no difference? Yeah, cool. Okay. So yeah, so this one is not a Nash equilibrium. So do people want to have a think about this and type in chat for rock, paper, scissors? If any two outcomes are the same, isn't it a Nash equilibrium? It isn't Nash equilibrium. Sorry, John, can you um explain a bit more what you mean? I don't understand. If any two probabilities are the same, it isn't a Nash equilibrium. Okay, 20 Lawsons. I think you need to think again. So you're saying rock, paper, scissors can't have Nash equilibriums because at least one person can always improve their result. So in the example I've got on screen right now, we have one third, one third, one third, v 0.1, 0.1, 0.8. Are you sure no one in this situation can improve their result? Yeah. So in the one on screen, just in case anyone hasn't spotted it yet, the one third, one third, one third player can improve their result by just always playing rock in this case. Yeah. Everyone who's answered seems to be saying correctly that the only equilibrium in rock, paper, scissors is the one third, one third, one third case. Yeah. So is that always true? Are there games with uh are there games with multiple equilibrium? Anyone think yes or no? Okay, lots of people saying yes. Can you give me an example if you think that's the case? A lot of yeses. Chess is a really interesting one. So in chess, we don't really want to talk about Nash equilibrium as like a way to solve the game because there's no randomness involved. Yeah, so I agree that games that aren't fully based off randomness, uh, I don't think we would talk about Nash equilibrium in those contexts, but I agree that they can have multiple optimal solutions. Okay, so let's just springboard off. Yeah, tic-tac-toe. Okay, lots of people are saying very interesting things. I'm going to talk about these. So games that have no randomness. I'm going to give you a very stupid game, and we'll talk about why it has multiple solutions, but they're all the same in this case. So let's say we have this little like tree shape, right? And we start here, and on each person's turn, we're going to alternate, and you get to choose if we go left or right down the tree. Okay. Uh, okay. So in this case, and the winner is just person two if they get to move to a W, or uh, person one wins if they get to the L. So who wins that game every time? Yeah, everyone's correctly saying player two. But the point I wanted to make here is that there are multiple like optimal solutions for both players. Like whichever decision player one makes, it doesn't matter, they still lose, but that's as good as they could do. So there are infinitely many Nash equilibrium in this case where player one goes with probability P to the left and probability one minus P to the right. So this game has infinitely many Nash equilibria. Does everyone believe what I said there? Okay, cool. Now, what was the other interesting thing people said? So tic-tac-toe. Yeah. So tic-tac-toe is an interesting one because there are all so in tic-tac-toe, all of the equilibria are going to lead to a draw because it's a guaranteed draw if both people play. What are the game's rules? Oh, are you talking? Oh, and are you talking about this game here on the left? It was just a silly game I just made up right now. It's just that on your turn you just choose which direction to go, and the player that if player one moves to a W, they win. If player one moves to an L, they lose. It was a silly made up thing. Um, anyway, so in tic-tac-toe, um, all properly played games should lead to a draw, but there are multiple ways to do that by like going in different rotations and reflections of the game. So even though there are many possible ways to play, they all lead to the same thing. So yeah, so there are many games with multiple equilibrium, which brings us to our next definition. Apparently it doesn't. Okay, this is the definition I wanted to make, which is a game with a unique equilibrium. That means there's only one. For example, rock, paper, scissors. That Nash equilibrium is called a strong equilibrium. And a game with multiple is called weak. Anyway, let's go back. So the main point of this part of the talk is this famous theorem by John Nash. Some of you might have seen the film A Beautiful Mind. It's about this guy, very well respected economist and such. But he has this cool theorem, which is that if we take any game, as long as there are finitely many players, i.e., there aren't infinitely many players, which is obviously a ridiculous concept anyway. And at each point in the game, the player can choose from only a finite number of options. Okay, they only have finitely many choices at each point. Then there is at least one Nash equilibrium. So it's saying every game under these conditions is going to have one of these equilibrium, which is kind of a crazy thing. So there is like going to be one of these like optimal configurations where no one can benefit by changing how they play. It doesn't say anything about whether it's a pure or a mixed strategy. So remember, mixed strategy means you do something random. Okay, everyone understand the? So Mohammed says even chess. Well, let's check. Does chess have a finite number of players? Yes, it has 2 players. At each point, can you only choose from a finite number of options? The answer is yes. So chess has a optimal solution. What we don't know is who wins in that optimal solution. So because chess is such an enormous game, we can't actually compute what the equilibrium is. So there's just too many possible games to check if white can always force a win or if black is actually able to draw the game. Does that make sense? Okay, cool. I'll maybe say something a little bit. So lots of people seem interested in the chess example. So chess, like this Nash's theorem, doesn't really make such good sense for chess. Because what chess basically is like a graph searching algorithm. So like imagine I'm going to draw a picture. This dot represents like the start position in chess. Okay. And now there are how many moves can the first player play? They can play 16 moves with their pawn or four. So the first person has 20 possible moves. Okay. And now each of these dots represent the board after that move is played. Okay. And then we can just like draw this whole tree representing all of the possible moves, right? Everyone happy with what I'm talking about so far? And then at the bottom of all of these trees, if we go down far enough, there are some situations where white wins, there are some situations where black wins, and there are some situations where there's draws. Okay? And in principle, to like solve chess, whatever that means, all you have to do is like trace back up the tree and decide like who won in each possible configuration, right? So let me draw like so if here is a situation where white wins, here is a situation where black wins, and we're at this node here, and we're asking if it's white's turn, does white win the game or lose the game? Well, of course, white wins, right? Because they can just choose to go to this direction. So we'll put a W here. Okay. Now suppose we have another node labeled black to win, and there could be a lot more tree underneath, and we've calculated up to black. And now we're at this node. Now, because we've gone up one layer, it's black's turn, which means that this whole tree becomes a black win, this whole part. Does everyone understand the kind of algorithm I'm describing? I can explain a little bit more if you want. So basically, in principle, using this is called minimax, actually. In principle, using this minimax algorithm, you could work back up the whole tree and just like you'll be left with one tip, the start, And this will either get labeled white, black, or draw. We don't know what it is because chess has not been solved because it's too complicated. But this is like, in theory, what you could do. Okay, that's the idea. Anyway, let's move on. So yeah, we've already said that rock, paper, scissors actually has a strong equilibrium. There's only one, and it's 1/3, 1/3, 1/3 for both people. So I guess that raises an interesting question of, are there games, similar games, where the equilibrium has different people playing different strategies? So in rock, paper, scissors, both people play the same. There probably are games where people play different. Maybe that's something for you to think about for yourself. Okay, we're going to do one more, and then we're going to move on to a new topic. So this, what's the equilibrium? Habton. Sorry, were you here for the first part of the talk? We're talking about Nash equilibria, which I defined earlier on. Um, I'll carry on for now, and if you missed it, maybe give it a Google. Okay, so Prisoner's Dilemma. So this is a new game. It involves two people. And like the backstory is we've got two prisoners, and they're being given a chance to like reduce their sentence, say. So they're taken into separate rooms, and they're offered a chance. They can either give up some information on their opponent, in which case they are going to get a reduced sentence, or they can just keep quiet and not say anything. Now, if they both cooperate, they end up in the same outcome, where they both have 1 year in prison. Okay, so if they both stay silent and cooperate with each other, they're each going to get 1 more year in prison. Uh, but if you keep quiet and your opponent gives details about you, you get 5 years in prison and your opponent goes free. Everybody happy with the setup? In the case when both people give up information, you're both going to get 2 years in prison. So the best possible outcome, I think, for everyone would just be to go into the both cooperate situation. But what we're going to do is we're going to analyze this in the Nash equilibrium kind of mindset. So we're going to try and calculate the Nash equilibrium for this situation. So I'm going to give you guys a couple of minutes. Feel free to write some equations down, or think about it however you want. So and then we'll talk it through in a moment. So I'm going to switch slides. So we're trying to choose a probability A of like cooperating and 1 minus A of not cooperating, and a probability B of your opponent cooperating. Trying to find values of A and B that make this a Nash equilibrium. Okay, some people are starting to answer already. I'm going to give everyone a minute. If you're a bit confused by this, don't worry. I'm going to explain how to calculate it in a moment. Yeah. So lots of people are saying the correct answer, which is that it's always going to be good to snitch. So the equilibrium is going to be A equals 0, B equals 0. Okay. So let's try and prove that. So imagine that we knew that our opponent was going to cooperate with us with probability B, probability they cooperate with us, and then with 1 minus B, they're going to snitch. Okay? So we want to choose the probability A that maximizes our expected score which means minimize the expected number of years we spend in prison on average. Everyone happy with the way I framed the question? So we want to choose our value of A if we knew our opponent was going to play B. And we're going to show that just like the best value is just going to be 0. Like we just want to play 0 every time. Okay, cool. So if we play A, what is our expected score? Well, using the formula for like expected value that we had the other day. So the outcome we have is, so when we snitch one minus A of the time, then when our opponent snitches as well, we're going to get minus 2 years in prison. And when they don't, we're going to get 0 years in prison. Okay, happy with that so far? And then when we keep silent, if our opponent snitches on us, we're going to get 1 minus B times 5 years in prison. And when they also keep silent, we're going to get 1 year in prison. So this is our expected score. And we want to maximize this over A. Everyone happy? We want to choose the A that makes our score as big as possible. And in this case, if you do some algebra and collect the terms and stuff like this, and you remember that B is going to be between 0 and 1, what you're going to come out with is that the way to do this is just to make A as small as possible. So you're just going to get A as 0. So to maximize your average score, no matter what your opponent is doing, you just have to snitch every single time. Which brings us to the concept of Pareto efficiency. So this is a new definition for you guys. So what happened in the prisoner's dilemma was that there was one Nash equilibrium and it was bad for everyone. So in the outcome, everyone just ends up getting 2 years in prison, when if they had cooperated, they would have just got 1 year in prison each. So it would have been better for everyone if we would have just... why is A 0 if we're trying to get the value as large as possible? Just like, just rearrange this formula. So we have basically the important term is that from these guys, we get a minus 5A, and then we get some like plus like 2A-ish, and then plus some constants that depend on B. So we get something like minus 3A plus stuff. And then to make minus 3A big, we need to make A small. That's the reason, just answering that question. Okay, so this is a definition that comes up in economics and stuff. You want to like allocate resources to the people who live in your town, country, whatever it is. And then an allocation is going to be Pareto efficient if there's no change you can make that increases some people's happiness without decreasing others. So in this case, the prisoner's dilemma equilibrium is not Pareto efficient because there is a change you can make, which is just going this way. And that makes everybody happier. Everyone happy with this definition? Everyone understand the point, why we care about this? Yeah. Okay, cool. So there's a pretty cool theorem which says, I'm going to define, first of all, a zero-sum game. So a game is zero-sum if the total score in every outcome is 0. So like there's a maximum of 0 points up for grabs. So an example is poker, where everything that you win is because your opponent lost. So the total profit of the group is 0. So in this case, prisoner's dilemma is not zero-sum because this adds up to -4, for example, not 0. This adds up to -5. So it's not zero-sum, so it doesn't apply. But there is a theorem that says for every zero-sum game, all of the Nash equilibria are Pareto efficient, which is pretty cool. Because we like Pareto efficiency because it's more fair and it achieves the best possible outcome for everyone. Okay. For the last 10 minutes of the talk, we're going to change lanes a bit. And we're going to talk about something completely different, which is now just a one-player game. So we're going to imagine that we're in a casino where we're being allowed to bet on the value of a biased coin. So this coin is going to come up heads with probability P. And it's going to come up tails otherwise, and that has probability Q, which is just 1 minus P. Okay, so think of like P being like 60%. So it's like in our advantage to bet on this coin. And now what we're allowed to do is for each flip, we can bet a proportion, which we're going to call F, of our current net worth. Our current wealth, we're going to call W. So W is how much money we have when we start the game. And we're allowed to bet a fraction of that on the coin. So first of all, should we guess heads or tails? And what does that decision depend on? Type it in the chat. Yeah, I agree. It depends on the value of P. And how does it depend on P? Yeah. So if P is bigger than a half, we guess heads. Cool. And then we'll be right with probability P. Nice. Okay. Now we're assuming that this bet is going to pay out B times the amount of money we staked. So for example, if we bet £10 and B was 2, then we get £20 out if we win. And if we lose, we just lose our £10 bet. So B is the odds we're getting on this bet. So if P is greater than a half, obviously we should just be like, if we want to maximize our average profit, we should just be betting as much as possible on every flip, because on average we're winning money. However, there's a problem in that like human beings can't do that because there's a non-zero chance that we'll just go bankrupt, and that's very bad. The reason is that our happiness isn't like a linear function of your like winnings from this game. It's actually going to probably look something more like a log curve. So if you won 10 times more, you would only be like 1 unit more happy. So the point of Kelly criterion is we're saying, okay, we want to maximize the log of how much money we get at the end of the game. What proportion of our current wealth should we bet on every flip? So the point is we're trying not to go bankrupt, basically. Because if we go bankrupt, we have minus infinity happiness, if that makes sense. Everyone happy with the question statement? Maybe it's a little bit unclear. So we're trying to maximize the average of the log of our capital after the game. Okay, I'm getting some yeses. People are a little bit confused. I think it will be clear when we are going through the calculation. So what we're going to derive is Kelly's theorem or Kelly's criterion, that the optimal amount to bet to maximize that is this quantity, which is P minus Q over B. So remember, B is the odds, Q is the probability of tails, P is the probability of heads. So for example, if the coin comes up heads 3/4 of the time, we should bet 3/4 minus 1/4 divided by, if it pays out 2 to 1, 2, which is whatever it is, 6/8 minus 1/8. So we should bet 5/8 of the amount of money we have every single time. So we're going to derive this formula. Okay. The derivation is a little bit tricky, but stick with me. So let's imagine that we start off with W0 money. This is like, you can imagine it's £100 or whatever it is. Now, we're going to play N rounds. And on each round, we're going to wager a proportion F of the money we have available at that time. Okay. Now, we should expect that we're going to win about NP rounds and lose NQ rounds. Does everyone believe that these are the average number of rounds we win or lose? Yeah. Okay, lots of yeses. Okay. So each time we win, the amount of money we have gets multiplied by 1 plus B times F. Okay. Do people believe this expression? Okay, good. So we win NP times. So we get multiplied by 1 plus BF to the N to the P. NP, sorry. Everybody believe that? And when we lose, our amount of money gets multiplied by 1 minus F. And we lose NQ times. Okay. So this is the average factor that gets multiplied onto our net worth. And we started off with W0. So this is the average wealth we have at step N. Okay. Happy with that so far? I'm going to use some index laws and just like rewrite this a little bit. 1 plus BF to the P times 1 minus F to the Q all to the N, right? So this is like the interest rate that we're earning on each flip, and we keep multiplying that. B is the ratio that we get paid out in. So if we bet £10 and B was 2, we get out £20. Okay, cool. So what we need to maximize is log of WN. Does everyone remember that? That's the goal. We're maximizing the log of our net worth. Q is 1 minus P. It's the probability of tails. Okay. So we're trying to maximize the log of this thing. Now I'm going to go on to the next slide. So I'm just going to use some log rules. So when you log WN, you get log of your initial value, which is just a constant, plus N times the log of 1 plus FB to the P, 1 minus F to the Q. And now using some more rules, it's the initial thing plus N times, okay, P log 1 plus FB plus Q log 1 minus F. Okay, everybody happy so far? And we're trying to maximize this over F. We're trying to choose the F that makes this as big as possible. So we're going to differentiate this with respect to F and then set equal to 0. So when we do that, we get this thing was a constant, so it's just 0. Then we get N times P over 1 plus FB times B. Don't worry about the details of this derivative if you haven't done lots of calculus yet. I'm just differentiating it. So we get Q times minus 1 over 1 minus F. And we set that equal to 0. We can cancel the N. And then when you rearrange this for F, you just get that F equals P minus Q over B. So what we calculated is that every guess we should be betting this proportion of our net worth on the outcome of the coin. Does everyone buy that derivation? Cool. So going back to the example I said here, so if the coin is heads with probability 75%, and you get paid out 2 to 1, then what this says is that you should bet 5/8 of your net worth on this flip every time if what you want to maximize is the average log of your final value. Okay. Cool. So the reason that human beings want to maximize the log of their final value, not their final value. Like if you would just say, well, why don't I just maximize the average final score I get? This doesn't really make sense because humans are pretty risk averse. Like humans are much more unhappy to lose money than they are to win money. So adding in this log, like, gives less reward for large wins and makes you more sad for small losses, which sort of lines up more closely with what human beings actually want to optimize.